Okay, this is one of those essay questions. I really don't like essay questions. They're usually 4, 5, 6, 7. Okay, using the principles of atomic and molecular structure and the information in the table below, answer the following questions about atomic fluorine, oxygen, and xenon, as well as some of their compounds. So it's first ionization energy is the energy necessary to remove the most loosely held electron or the valence electron. So it takes more energy, or it's more difficult to take a valence electron away from fluorine than it does from oxygen. Okay, so that's this page. Okay, second question. Write the equation for the ionization of atomic fluorine. Okay, so here's the deal. It said equation. It did not say thermochemical equation, so let me do this. Here is the equation. You take fluorine, gas. It can't be F2. It has to be a single atom in the gas state. And then what happens is you zap it with some energy, and it's 1,681 kilojoules per mole, and you make an F plus 1 gas ion, and you kick off 1 electron. Some things you should notice: charge over here is 0, positive 1, and negative 1 is 0. By the way, it's okay if you just put a plus here. This is the first ionization energy for atomic, not molecular fluorine. Has to be in the gas state. That makes everything equal. So like, it takes energy. Like if you were doing sodium, it takes energy for sodium to go from a solid to a liquid to a gas. And so sodium solid to liquid is melting, heated melting. And then sodium liquid to gas is heat of vaporization. And then sodium atom to sodium ion is ionization energy. The other thing I want you to see is that, again, this is called ionization energy. It's how much energy does it take to turn an atom into an ion. And if we've talked about PES up to this point in this course, you can kick out any electron. The one that's the easiest to get is the valence shell, and so the one that has the lowest energy when you do PES is called the ionization energy, or the first ionization energy. Okay, account for the fact that the first ionization energy of atomic fluorine is greater than atomic oxygen. Here's the deal. Why is it harder to get an electron away from from fluorine than it is from oxygen? You need to put a lot more energy in, or roughly 350 more kilojoules to get the first electron away from fluorine and oxygen. Now, and it says you must discuss both atoms. So what it would say is, now remember, you always answer the question first, but this is an essay. And the essay template is, remember now, first step in every essay is you have to find the 2 atoms on the periodic table. So here's oxygen is atomic number 8. Fluorine is atomic number 9. They're both in the second row or the second period. And so what you do is, if they're in the same row, you don't talk about shells and shielding electrons. You talk about effective nuclear charge. So we are going to we're going to answer the question first. And then in the explanation, we're going to talk about the fact that fluorine has a higher effective nuclear charge than oxygen. By the way, these are not their effective nuclear charge. You don't have to say what this is, but effective nuclear charge is the atomic number minus the shielding electrons. So this has an effective nuclear charge of 7, and this has an effective nuclear charge of 6, because the 1s orbital, it holds 2 electrons. But you can just see that if they're in the same row, the valence electrons are or the shielding electrons are the same. So the one that has the greater number does have the greater effective nuclear charge. Okay, so let me just, and then when you're done with that, so effective nuclear charge, which I call ZEF, Z because that's atomic number, EFF is atomic number minus the shielding electrons. And then you have to connect that to Coulombic attraction. And Coulombic attraction is a force, so we say stronger. We use the term stronger, weaker. And then you don't really have to do this, but I think that I've noticed that my students get more points if they do. Coulombic attraction, you should talk about that, how that affects the pull on the valence electrons. And then finally, how that affects either radius, if it's a radius question, or IE, ionization energy 1. So here's the thing. So so this is the template. And then the thing that I want to tell you is, in this case, because the way the question's asked is account for the fact that the first ionization energy of fluorine is greater. So we always should be talking about why fluorine is greater, not why oxygen is smaller or less than, because answer the question the way it was asked. And this is, again, what we're going to do is fluorine has a larger Zeph than oxygen. That means it has stronger Coulombic attraction. And this causes holds valence electrons tighter. And then this results in more energy to remove a valence electron. Okay, so having said all that, now I'm going to see if I can answer this question. I'm going to add a page here. So, and they said talk about each. So in the first sentence, I would say fluorine, and they're actually okay with you just putting F, has a greater effective nuclear charge than oxygen. They want us to talk about both. Okay, this is really bad writing. I apologize. It's like my cord is sitting on top of the dealio that I'm writing on. Okay, and then you'd say something like therefore, hence, I don't care your favorite linking word. Therefore, fluorine has a greater Coulombic, they love Coulomb's law. Sorry, I probably should spell Coulombic right. Greater Coulombic, sorry, I didn't say greater, I said use stronger, has a stronger Coulombic attraction for its valence electrons than oxygen. Because the because the valence electrons are held more tightly, this results in needing more energy to remove a valence electron. Something like that. I don't actually care about the grammar. You just have to talk about ZeV, or shells and shielding electrons, Coulombic attraction, force of attraction between the nucleus and the valence electron, and energy or radius or whatever. Okay, predict whether the first ionization energy of xenon is greater than, less than, or equal to the first ionization energy of atomic fluorine. Okay, this one you don't know. If you go back, there's a question mark here. We don't know, but here's what I would say to you, and this question is kind of tricky because most people say xenon, and it's not true. Here's fluorine, row 2. Here's xenon, row 5. Okay, if it was neon, I'd say neon, but remember I said the shells and shielding electrons, so there's one difference on ZeV. There's 3 shells difference on xenon. So in what we're going to say is I would go with the shells and shielding electron argument. Let me say why that is again. These are both in row 2, and so this is atomic number 9, this is atomic number 10, this has slightly greater ZeV. Going down, though, this is row 2, this is row 5. That's 5 whole shells. And the other thing is the up-down trend is stronger than the left-right trend. And so here's my template. I'm not answering this yet, but when I do this, here is my template. Switch colors. I'm going to say xenon something like the IE1, I'll write it out, of xenon is less than fluorine. Okay, I'm going to write that nicer, but you got to answer the question first. And then we're going to talk about shells, shielding electrons, how this affects Coulombic attraction, again, stronger, weaker, how this affects pull on valence electrons, and what this means in terms of the first ionization energy. Okay, there's our template. I'm going to add a new thing. So here's what I would say. I'll try to be a little nicer here. Going back, I would say, oops, wrong way. Sorry. Something like the first ionization energy of xenon is less than the first ionization energy of fluorine, which people don't usually bite on this because of the whole noble gas thing. Now here's where I say, so then we're going to answer this question in term of less than. Next sentence, xenon has more shells and more shielding. Oh, sorry. Okay, I can be nice. This is a tape. You can fast forward. More shielding electrons than fluorine. Now remember, Coulomb's law says that the force, I'm going to erase this, but the force of the attraction is proportional to Q positive, Q negative over distance squared. And because the distance is squared, that's why this trend is stronger. And So what happens is, though, when you divide by a bigger number, because xenon is bigger, when you divide by a bigger number, it makes the force of attraction or the, smaller. And so the first sentence is, or first part is this, always go to Coulombic attraction. The Coulombic attraction, or therefore something like that, between, I probably should say this, the nucleus and the valence electrons in xenon is weaker. Thus, therefore, hence, the valence. And we probably should talk about both. Give me just a second. Let me just back up. The force of the Coulombic attraction between the nucleus and the valence electrons is weaker than in fluorine. And then we would say xenon's valence electrons are not held as tightly, so it takes less energy to remove a valence electron. Usually by the time I give you this, you've had lots of practice. All right. Xenon can react with oxygen, fluorine, blah, 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 and the boxes provided below. Draw those. Okay, so here we go. XeO3, I didn't put the boxes here, but this is what I would do. I'd go xenon. There's no Habib. I will put these things evenly spaced. This guy has 2. It wants 8. I'd add 6. This guy has 2. It wants 8. I'd add 6. This guy has 2. It wants 8. I'd add 6. Xenon has 2, 4, 6. It wants 8. When I do ORP, I get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons. When I do VE, I get 8 plus 6 plus 6 plus 6. 6 times 3 is 18. 18 and 8 is 26. That's beautiful. That means this picture is right. It's an AB3E. Didn't ask for that, just said drew the picture, but we're going to come back. Okay, now I need to do XeF4, which I think is the more interesting one, but still XeF4. So I would do Xe. I would add F, 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 F. This guy has 2. It wants 8. So I'd add 6, add 6, add 6, add 6. Looking at xenon, 2, 4, 6, 8. So when I do ORP here, octet rule prediction, that means you only have single bonds and every element has exactly an octet. I get 6 and 6 and 6 and 6. 6 times 4 is 24, 26, 28, 30, 32. ORP is 32. VE is going to be 8 plus 7 plus 7 plus 7 plus 7. 28 and 8 is 36. And so our picture is not correct. And because ORP is less than VE, that means we have too many valence electrons, and so we have to add some dots. I'm going to switch pen color so that you can see the difference. The real structure is you have to add 4 dots. And so what happens is this ends up being an AB4E2. All right, so having said that, all you got to put in the boxes are those 2 pictures. And then on the basis of what is the geometric shape of the Xe, so I'm going to answer the question. It is trigonal, pyramidal. Let me just explain why. If you have an AB3E1, what you do is you start out with the tetrahedral, which is 1, there's the central, 1 goes up, and then the other 3 come out like the legs on a tripod. And then, so I'm trying to draw this, and like if you can look at this, little shape here. And basically, if you remove one, watch me erase it, it's not tetrahedral anymore. This shape is called trigonal pyramidal. And if you take the time to draw it, so what happens is there's your triangle base, there's your pyramid. What is the hybridization of the valence electron? So here's the deal. XeF4, you can see from the picture, is AB4E2. 4 plus 2 is 6. So you have to have a hybridization that involves 6 orbitals. So it's sp3d2, because 1 plus 3 plus 2 is 6. So remember that you got sp, that's when these add up to 2. You got sp2, that's when these add up to 3. You got sp3, you got sp3d, that's when they add up to 5, and you got sp3d2. All right, that was a fairly long one. Oops. Predict whether this will be polar or nonpolar. I predict, answer the question, XeO3, the XeO3 molecule is polar. Why? It has 3 polar covalent bonds which are asymmetrically arranged, which is these are the 2 conditions. You don't have to write this. I'm just doing this so you guys learn this stuff. These are the 2 conditions necessary for a molecule to be polar. All right. I think that's it now.